In a previous video, we defined the sine function and we defined the cosine function. And if you recall, we related those to a point on a circle, and the cosine specifically was the ratio of the x value of the point over the radius of the circle, and the sine was the y value of the point over the radius on the circle. So we are going to define 4 other trigonometric functions that we're going to want to be conversant in. And so we'll introduce those here. All right, so the 4 functions are the tangent, the secant, the cosecant, and the cotangent functions. All right, and so just as a reminder, right, so the sine of theta is y over r in this picture, and the cosine of theta is x over r. So we define these other trigonometric functions in similar ways. So the tangent is going to be the ratio of the y value of the point to its x value. The secant is going to be the ratio of the radius divided by the x value. The cosecant is going to be the quotient of the radius over the y value, and the cotangent is going to be the x value divided by the y value. Now, what's going to be really useful for us is to understand how these 4 new functions relate to the 2 we've been working with, the sine and the cosine. So the tangent of theta we can think of as just simply the sine of our angle divided by the cosine of our angle. All right, to make sure we understand why this is, on the previous page we defined the tangent to be the quotient of y over x. But of course, if I'd like, I could divide both the top and bottom of this fraction by the radius of the circle that I'm on, and I haven't changed the value of the fraction. But of course, I know that y divided by the radius is just the sine of theta, and x divided by the radius is just the cosine of theta. And so that's where this relationship here comes from. All right. Then we have the secant of theta is equal to 1 over the cosine. All right. So on the previous page, we defined the secant of theta to be r over x. But just understand this is the reciprocal of x over r. And x over r we know is the cosine of theta, so the reciprocal would be 1 over the cosine of theta. And a similar derivation, of course, shows that the cosecant of theta is 1 over sine of theta, and that the cotangent of theta is, on the one hand, the reciprocal of tangent of theta, but on the other hand, we could say then it's the cosine of theta divided by the sine of theta. Okay. Now, one thing I should point out is that there's kind of an annoying mismatch here in the naming of these trigonometric functions. So here's what I want you to notice is that cosine goes along with this new trigonometric function which does not have the word co in it, whereas the sine goes along with this new trigonometric function that does have the word co in it. Okay, so it's kind of the opposite way that you would wish it would work. It would be kind of nice if cosine and cosecant went together and sine and secant went together, but they don't. It's exactly the opposite. So just do your best to remember that, and if anything, just remember that it's the opposite of how you'd probably like it to work. Here we'll take a look at an example where we're asked to evaluate a couple of these new trigonometric functions. So let's start with the secant of 2 pi over 3. So here's a chance for us to use that memory device that we learned about, that for secant and cosecant, they're kind of defined in the opposite way you might think they are. So, while it might seem to make sense that secant would go with sine, no, it goes with cosine. So it's 1 over the cosine of 2 pi over 3. So let's find 2 pi over 3 here on the unit circle. So if I broke pi, which is half the circle, into thirds, it'll look something like that. So there's pi over 3, 2 pi over 3 is here. All right, so we're interested in what is that point right there. And clearly this should be one of those situations where the y values, absolute value, is bigger than the x's, okay? And in terms of the special angles we know on our unit circle, that happens when one of them is 1/2 and the other one's root 3 over 2. So root 3 over 2 is definitely bigger than 1/2. So the x value here is the shorter side, so that should be my negative 1/2, negative because it's in the second quadrant. And the y should be root 3 over 2. But for this one here, the cosine is the x value, so we know that this is 1 over negative 1/2, which is just 1 divided by negative 1/2, which is equal to 1 times the reciprocal, negative 2 over 1, which would equal negative 2. And of course I showed a lot more detail here than is generally necessary, right? Typically once we set this up, we're usually pretty comfortable jumping just straight to the top times the reciprocal of the bottom, and just jumping straight to negative 2. But let's go ahead and take a look at the cotangent. The cotangent of 2 pi over 3. So we define that as the cosine of 2 pi over 3 divided by the sine of 2 pi over 3. So that's just going to be the quotient of those two values there, where I put negative 1/2 on top and square root of 3 over 2 on bottom. And I'll go ahead and show a little more detail on this first example. So that's negative 1/2 divided by square root of 3 over 2, which is negative 1/2 times 2 over the square root of 3. And those cancel and give me negative 1 over the square root of 3. And I am completely fine with you leaving answers this way. I don't need you to rationalize the denominator, but what is important is that if you're working on problems from the book, and let's say the book does rationalize the denominator when it shows the answer in the back, you need to know when your answer is the same as what the book has. So let's just remember that you can always take negative 1 over root 3 and multiply the top and bottom by root 3. And the square root of 3 times the square root of 3 is just 3. And then on top, of course, we just have root 3. So this would also be a valid way of writing it, and that may be how the answer is written in some cases. But again, I'm fine with you leaving it this way. In this example, we'll look at one where we're working in degrees instead of radians. So first of all, where is 330 degrees? Well, 360 degrees is 1 full revolution. So if I just back off 30 degrees, that puts me right about there, then I know that's the 330 degree angle that I'm interested in, going from standard position all the way around to 330 degrees. So when I'm thinking of the tangent of 330 degrees, in the previous problem, I used the strategy of saying that the tangent is the sine divided by the cosine, right? And we said that the secant was 1 divided by the cosine. So I related it back to sines and cosines. But also, just let's not forget that we can also think of the tangent of 330 degrees as the y value divided by the x value of the point associated with that angle. So of this point right here. And I think in this case, that's kind of a convenient way to look at it. So as I look at where I'm at on the unit circle, and I understand that I have this reference angle of 30 degrees here, I know that I'm basically forming this triangle to figure out what my point is. Okay, and so I know that the longer side here is my x, the shorter side's my y. Clearly the x is positive and the y is negative, so this is going to give me negative 1/2 divided by positive square root of 3 over 2, which is negative 1/2 times the reciprocal of the fraction down here, so times 2 over root 3. And I can see my 2's canceling, and I end up with negative 1 over the square root of 3. And I could go back to the basic definition to figure out the cotangent of 330 degrees, but let's also understand that if I want the cotangent of 330 degrees, but I've already determined the tangent, I can just use the property that the cotangent is the reciprocal of the tangent. Which, understand, the reciprocal just means the flip. So I suppose I could put negative 1 over root 3 in this spot here, but I also could just be slick about it and say, I'm going to take my answer from tangent of 330 degrees and flip it. So that's just going to give me square root of 3 over negative 1, which of course I'm not going to leave it that way. I'm going to get negative square root of 3. All right, in this example, we're going to do one more evaluation, but this time at negative 9 pi over 4. Now notice negative 9 pi over 4 is not between 0 and 2 pi, so it's not within that first revolution around a circle that we're used to dealing with angles in. But let's remind ourselves of the concept of coterminal angles, right? I know that if I can find coterminal angles to negative 9 pi over 4, that those angles end in the same spot on the circle as negative 9 pi over 4 does. And of course that would mean that any trig function at that value would be the same as at negative 9 pi over 4. And so remember, what we do is we can just add copies of 2 pi, right, or of one revolution to negative 9 pi over 4, and that'll give us coterminal angles. So the only question here is, how many copies of 2 pi do I add? And remember, the little computation that might be kind of nice to do is just to say, what is negative 9 over 4? Well, that equals negative 2.25. So I can see that if I added 2 pi to negative 9 pi over 4, that would not quite get me above 0. So that tells me to add 2 copies of 2 pi. So of course that's negative 9 pi over 4 plus 4 pi. And then to get common denominators here would be negative 9 pi over 4. Multiply the top and bottom here by 4, gives us plus 16 pi over 4, which gives me 7 pi over 4. So what we can say here, I'll say it up here, is that negative 9 pi over 4 and 7 pi over 4 are coterminal. Now I know 7 pi over 4 is right here on the unit circle because 8 pi over 4 would be 2 pi, and then let's just back off one of those, or 1 pi over 4 to get to this spot, and that gives you 7 pi over 4. All right, so let's take a look at the cosecant here. So first I'll note that the cosecant of negative 9 pi over 4 is exactly the same as 1 over the sine of negative 9 pi over 4. Right? But then also, because negative 9 pi over 4 and 7 pi over 4 are coterminal, I can also say that this is the sine of 7 pi over 4. Okay, so the sine of 7 pi over 4, what's that? Well, remember all the multiples of pi over 4 are the ones where the x and y values are actually exactly the same. These are supposed to be the same here. So that should ring a bell to be root 2 over 2, but since the y value is negative, this is negative root 2 over 2. And then also, I suppose what is worth remembering is that root 2 over 2, remember, is the same as 1 over root 2. And negative 1 over root 2. So this is an equivalent way of writing that point. And the reason I bring that up here is because I can see that I'm going to be taking the reciprocal of the sine of 7 pi over 4. Well, the sine of 7 pi over 4 could be expressed either this way or this way. And so you have your pick. And so, you know, if I was thinking ahead here, what I would probably do is I would probably pick negative 1 over root 2, take its reciprocal, which is just going to be negative root 2, just because this is really easy to flip over. Okay, now of course it's still perfectly correct to use this. It's not a big deal, but just kind of a little note that it's nice sometimes to be interchangeable with the way that we express those values at multiples of pi over 4. So I get negative root 2 for the cosecant of negative 9 pi over 4. And then the tangent. Okay, now the tangent, I'm going to be a little more slick with this one. Okay, so I could definitely think of this as the sine over the cosine, right? But let's just first make a little note that this is the tangent of 7 pi over 4. That's the same as the tangent of negative 9 pi over 4. But this time I'm going to use this definition here. Y over x. And the reason I want to use that is because I can see that I'm just at this really nice value where the x and the y are the same except for maybe a sine. So I don't even have to think about this one too hard. I don't even have to mess with the root 2 over 2's or the 1 over root 2's. The idea is if the x and y's are the same, then of course y divided by x should just give you 1. But because of the fact that I know that the x value in this instance is positive and the y value in this instance is negative, instead of getting 1, I'm of course going to get negative 1. All right. So of course there's nothing wrong with, you know, putting in the actual y value, putting in the x, and showing the cancellation, or turning this into sine divided by cosine and doing a similar thing. But hey, whenever you can take shortcuts, take those. And in this case, we can immediately jump to saying that the tangent is negative 1. All right, I want to do 2 more examples, but this time we're going to focus on a couple of, I guess, would be maybe even easier angles. So we'll look at pi over 2, but I want to do all 6 trigonometric functions evaluated at pi over 2. All right, so of course at pi over 2, we're talking about this point right here. So let's start with sine. The sine of pi over 2. Okay, well, again, let's think about the unit circle. If we were on the unit circle, clearly the y value at that point would be 1. And so the cosine would be 0. All right, so now let's go down the list here. The tangent of pi over 2, well, let's use the definition that that's equal to the sine divided by the cosine. And we just computed both of those, so I can pencil in. This is 1 over 0, okay, but of course that should set off some real red flags, right? The one thing we know we can't do when we're looking at fractions is divide by 0, right? That's really bad news. So this is bad, okay? So here what we would say is, since this can't be done, we say that the tangent of pi over 2 is undefined. Okay, and that shouldn't throw us off too much. Think about functions that you looked at in the past, because remember, tangent is just a function. If I had 1 over x, we would realize that, x cannot equal 0. So when I'm thinking about tangent, I know that, okay, I cannot allow pi over 2 to go in this function, just like I can't allow 0 to go into this function. All right. Well, okay, the tangent is clearly undefined. What about the cotangent? All right, the cotangent is the cosine over the sine. All right, so playing the same game here. The cosine is 0, the sine is 1. Is that allowed? Well, certainly that's allowed, right? You can take 0 divided by 1, and you do get a number. You just get 0. Okay? So the cotangent is defined at pi over 2, and it's a value of 0. All right, so let's look at our other two here. The cosecant of pi over 2. Right? What is that? That's 1 divided by the sine of pi over 2. But the sine is 1, so I get 1 over 1, which equals 1. Okay, so the cosecant of pi over 2 is 1. And then finally, the secant of pi over 2. Right? We know the secant is 1 over the cosine of pi over 2. Oops, big vertical lines back. All right, fix my pi there. Okay, so 1 over the cosine of pi over 2, but that's what? 1 over 0 again, right? Just like for tangent. So we've got problems again, right? Don't want to be doing that. So here we would say the secant of pi over 2 is undefined. So at this spot here on the unit circle, we have 2 of our 6 trig functions actually end up being undefined. All right, here I'd like to evaluate all 6 trig functions again, but let's do this at theta equals pi instead of pi over 2, which is right there. All right, so let's go through the list here. Sine of pi, we'll go through these rather quickly. The sine of pi is 0. The cosine of pi, of course, is -1, right? All right, so as we go through here, maybe I should be suspicious here. Tangent is where things went wrong at pi over 2. So the tangent, right, is the sine over the cosine. The sine is 0. Cosine is -1. Okay, but that's fine, right? 0 divided by -1 is still 0. So that is defined this time. So you might suspect then cotangents where we're going to run into trouble. So the cotangent of pi, right, that's the cosine of pi divided by the sine of pi, and right, we're having a 0 in the denominator as a result, right? So we're trying to put -1 over 0. We know that that can't happen. So this is going to tell us that the cotangent of pi is undefined. All right, and then our we're doing the other 2 here. So the cosecant of pi, right, being 1 over the sine of pi, and I can already see I've got trouble because it was the sine of pi being in the denominator that gave me trouble before. 1 over 0 once again is going to spell disaster. So we would say that the cosecant of pi is undefined as well. But the secant isn't going to give us any trouble at all because that's going to cause the cosine to be in the denominator. And the cosine isn't 0. So this shouldn't be a problem at all. It's 1 over negative 1, which of course I will simplify to negative 1. So again, I've got 2 of the 6 trig functions being undefined here. The other 4 are okay. Lastly, we're going to talk about approximating these new trig functions using our calculator. So we're going to look at the cosecant, the cotangent, and the secant in this example. But what we should notice first is that when we look at the calculator, we see sine, cosine, and tangent buttons, and that's it. So we don't have a cosecant button or a cotangent button. So what we need to do is use the relationship we know that these functions have to sine, cosine, and tangent in order to be able to make these approximations. So let's start with cosecant, right? I know that the cosecant goes along with sine, right? It's the reciprocal of sine. So this is really 1 over the sine of 0.7. And remember that if you have a number inside the argument of your function and it doesn't have a degree symbol, you can assume it's in radians. So I'll go over to my calculator. I will make sure that I'm in radians, which I guess I'm not. So I'll go down and switch to radians in mode. And I'll quit. And now I'll just type in 1 divided by the sine of 0.7. And that'll give me my approximation here if I want to round to the nearest hundredth. That would be 1.55. All right, so let's take a look at the cotangent. The cotangent of 1.2. Well, we can relate this back to either sine and cosine or tangent, right? We know that it's the cosine over the sine, or we also know it's 1 over the tangent. So it seems to me calculating 1 trig function is easier than calculating 2, so I will use the property that it is 1 divided by the tangent. So still in radians, 1 divided by the tangent of 1.2. So we get 0.3887795 and so on. So if I'm rounding the nearest hundredth, right, we got to be careful to do our rounding properly, right? We can see that we have in the hundredths place an 8, but then in the next place, in the thousandths place, another 8, so it rounds up. So my approximation would be 0.39. All right, then lastly, let's look at the secant. We know that the secant is 1 over the cosine, so I'll rewrite this as 1 over the cosine of 49 degrees, but I'm also noticing that I'm back in degrees, so I remember to switch my mode back into degree mode before I actually type that in, and now I can say 1 divided by the cosine of 49. So that'll round to 1.52.